Then frequency changing means what? Source, we are changing the source from one sodium vapor lamp to mercury vapor lamp, like that. Frequency changing means we are actually changing the source. Source itself we are changing. So, effect of frequency. So, the higher frequency, threshold frequency, we know less than the threshold frequency, if light is incident, no electrons will be ejected. Less than the threshold frequency, if light is incident, no electrons will be ejected. Then there is no question of stopping the electrons. So, what is from that? What you know? There is a minimum frequency below which there is no emission of photoelectron, and therefore no need of stopping potential. We are studying frequency and stopping potential. See, so when we increase the frequency, see, we know there is a minimum frequency to eject electron from a metal surface. Suppose the ray which is incident is having higher frequency. What will happen to the remaining energy? Have you thought of that? What will happen to the remaining energy? Minimum energy is used to eject electron. What will happen to the remaining energy? It will be used to give kinetic energy to the electron. So, the minimum energy it uses to eject electron, and the remaining energy, minimum energy, for example, h nu is the energy incident, h nu. And in that h nu 0 is the energy required to eject electron, work function of the metal or threshold energy of the incident radiation. H nu 0 is the energy used to eject electron, and there is more energy because frequency is greater than the threshold frequency. So what happened? Remaining energy is utilized as kinetic energy. So if frequency is more kinetic energy, the electrons will move. With the greater kinetic energy, electrons will move. So stopping potential needed is large stopping potential is needed. Frequency is increased. That is happening when frequency increases. I will show the graph. This is the graph of for that frequency stopping potential. So, if frequency is less than threshold, this region shows that less than threshold frequency, there is no emission of electron. See, light is incident, but there is no emission of electron. So, there exists a minimum frequency. How will you explain this graph? So, you can see the emission for the metal A, the stopping potential is required only after certain frequency. What is the meaning of that? For the given metal, for this metal, there exists a minimum frequency, nu 01. Below that, there is no emission of electron. There is no need of stopping potential to stop them. But you see, when we increase the potential, see this point, you think, frequency is here, and then stopping potential is needed. You can take this point, frequency is here, stopping potential is here. So stopping potential is needed and is directly proportional. See, above the threshold frequency, what we can see? Above the threshold frequency, what we can see? Directly proportional frequency of the radiation. See, this is the frequency of radiation. As the frequency of the radiation increases, stopping potential also increases because the extra energy that is converted into kinetic energy. So with greater kinetic energy, that means greater stopping potential is needed. The reverse potential is needed to stop them. So that is the explanation of this graph. So below the threshold frequency, no emission of electron, stopping potential is 0. Above the threshold frequency, what happened? Linear variation. Frequency increases, stopping potential also increases because when frequency increases, kinetic energy increases. So more stopping potential is needed. This is reverse potential actually. Greater linear variation we can see. And another metal, you see, we have studied it for another metal. And there you see the threshold frequency is greater for this metal, this much frequency is needed. But if this is 300 raised to 14 hertz, this will be 500 raised to 14 hertz frequency. So this require a greater value of threshold frequency. That is the meaning of that. Greater value of threshold frequency. Then only electrons will be ejected from this metal. The other variation is similar. When we increase the frequency, stopping potential also increases. So this is the explanation of this graph. And you know that when we extend this graph, we will get a intercept on the y-axis, and that y-intercept will give the work function of the metal minus 501 by E, and that I will explain in another graph. Okay, that we will explain later. Okay. Now we are studying the experimental behavior. So that means study. Okay. Next, about this, I think you understood. I'll ask a question whether you understood or not. You should know. For which metal is having greater threshold frequency? Arunjit, which metal is having greater threshold frequency? Arunjit.
Yes, teacher.
Which metal is having greater threshold frequency? Which metal needed greater threshold frequency? From the graph, tell.
Metal. Metal, teacher.
Metal?
B.
B, correct. And this much frequency is needed. Okay. Then after the threshold frequency, when the frequency of the radiation is greater than the threshold frequency, what is the behavior? How are they related? Stopping potential and frequency, how are they related? Anasham? If the frequency is greater than the threshold frequency, what is its relation with stopping potential? Anasham? Anasham? When we increase the frequency, how is it related to stopping potential? Tell. Okay. Ashley? 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 Abhinav? Abhinav ഇപ്പോൾ ഒന്നും മിണ്ടറില്ല കേട്ടോ. അഭിനവ് ഒരു കാര്യം ചോദിച്ചാൽ ഒന്നും പറയില്ല. അഭിനവ്, ബാക്കിയുള്ള കുട്ടികളൊക്കെ പറയുന്നുണ്ട്. നിഹാല പറയട്ടെ. നിഹാല, when the frequency is greater than the threshold frequency. നിഹാല. ഭൂമിക. ഭൂമിക, അയ്യോ എൻ്റെ സമയം മുഴുവൻ പോണു. ചുമ്മാ വിളിച്ചു ഞാൻ പറയാം. When frequency increases, what happen? The linear variation increase. Frequency increases, stopping potential also increases. അതാ ഇവിടെ ഈ പോയിന്റ് എടുക്കുക. ഇവിടെ ഫ്രീക്വൻസി, സ്റ്റോപ്പിംഗ് പൊട്ടൻഷ്യൽ. ഈ പോയിന്റ് എടുക്കുക. ഇവിടെ ഫ്രീക്വൻസി, സ്റ്റോപ്പിംഗ് പൊട്ടൻഷ്യൽ. അപ്പോൾ ഫ്രീക്വൻസി കൂടി, സ്റ്റോപ്പിംഗ് പൊട്ടൻഷ്യൽ കൂടി. ലീനിയർ വേരിയേഷൻ ആണ്. മനസ്സിലായില്ലേ? വൈ ഇന്റർസെപ്റ്റ് കണ്ടാൽ എന്താ കിട്ടുക? It gives the work function of the metal. വിളിച്ച് എൻ്റെ സമയം മുഴുവൻ പോകാൻ. എന്നിട്ട് പറഞ്ഞിട്ട് കാര്യമില്ല. ഒന്നും ശ്രദ്ധിക്കില്ല എന്നുള്ളതാണ്. ബോയ്സ് ആണ് ശ്രദ്ധിക്കുന്നത് നല്ലത്. അവർ എന്തെങ്കിലുമൊക്കെ പറയുന്നു. ഗേൾസ് ഒന്നും ഒരു അക്ഷരം ഇട്ടില്ല. കുറച്ച് കുട്ടികളുണ്ട് നല്ലത് പറയുന്നത്. പിന്നുള്ളവരൊക്കെ വെറുതെ ഇങ്ങനെ ഇരിക്കുകയാണ്. ക്ലാസ് ശ്രദ്ധിച്ചൂടെ നമുക്ക്? അപ്പോൾ effect of frequency of the incident radiation. If photoelectric current frequency തമ്മിലുള്ളതാണ്. ഗ്രാഫ് കാണിച്ചിട്ട് നോക്കാം. ഗ്രാഫ് നോക്കാം. പൊട്ടൻഷ്യൽ നേരത്തെ പറഞ്ഞില്ലേ, പൊട്ടൻഷ്യൽ കൂടുമ്പോൾ നമ്മൾ പഠിച്ചതാണ്. പൊട്ടൻഷ്യൽ, വെൻ വി ഇൻക്രീസ് ദ പൊട്ടൻഷ്യൽ, എ ഈസ് മെയ്ഡ് മോർ ആൻഡ് മോർ പോസിറ്റീവ്. ബട്ട് വി ഹാവ് സീൻ ദ photoelectric current increases and reaches a saturation value. that we have seen. And reversing the potential, we have seen a minimum potential is required to stop the electron, that is the stopping potential. So for the frequency nu1, for the radiation of frequency nu1, what we have seen, first when we increase the potential, photoelectric current increases and reaches a constant value. Straight line path constant value. That is a saturation value, saturation current. So first when we increase the potential of plate A, made more and more positive, as the potential increases, photoelectric current also increases, reaches a maximum value or a saturation value. Then we study by reversing the potential. When you decrease and reversed. Reversing the potential at a minimum value of potential, all the ejected electrons are stopped. That potential is known as stopping potential. This is the graph for that. And second graph also we have seen the saturation current is same because we are not changing the intensity. We are not changing the intensity. When intensity changes, then only that saturation current will be different. We are only changing the frequency. For example, different source, we are changing the source only. Greater frequency we have experimented. And greater the frequency, we have seen greater the stopping potential, because greater is the frequency, kinetic energy will be more, because the minimum energy it will take to eject electron, and the remaining energy it is converted into kinetic energy. So greater value of frequency, that means greater reverse potential is needed. For example, -3, -5, -7, like that, negative potentials are required to stop that. And all these factors studied are given as laws. So if you know this one, the laws are very simple. First law we can see. For a given metal and frequency of the incident radiation, the number of photoelectrons ejected per second is directly proportional to intensity. That was the first experimental study. As the intensity increases, photoelectric current increases. That was the first experimental study. Intensity increases, photoelectric current increases. See how the intensity and photoelectric current are related, directly proportional. Number of photoelectrons ejected per second, that means number of photoelectrons ejected per second. What is the meaning? That is total charge by time. Total charge by time is current. So this is photoelectric current. Photoelectric current is directly proportional to intensity. Remember, photoelectric current in the intensity, they are directly proportional. Okay, second law. First density is proportional to photoelectric current. Density proportional to photoelectric current. Second, for a given metal, there exists a certain minimum frequency. So for a given metal, there exists a certain minimum frequency of the incident radiation, below which no emission of photon. That just now we explained. There exists a minimum frequency of the incident radiation, below which no emission of photoelectron takes place, and that frequency is called threshold frequency. But what is second law? There exists a minimum frequency of incident radiation, below which there is no emission of photoelectron, and that frequency is known as threshold frequency. Second law. See, that also we have studied in that experiment. Then the third one, if less than the threshold frequency, no emission of electron. Then greater than the threshold frequency, what happened? That also we have seen. Kinetic energy of the electron increases, and that is proportional to frequency. Kinetic energy of the electron is proportional to frequency, independent of intensity. That is the third one. So this is less than the threshold frequency. There is no emission of electron. Above the threshold frequency, kinetic energy is proportional to frequency. That is third law. Kinetic energy of the electron is directly proportional to frequency. And third law. The last law, the photoelectric emission is an instantaneous process. Just when a photon is incident, an electron is ejected. So that is an instantaneous process. Time lag, very small, 10 raised to minus 9 seconds. You see, 10 raised to minus 9, very, very small quantity, isn't it? 1 by 10 raised to 9, 1 divided by 10 raised to 9. That's such a small instant of time is only needed for this incidence of photon and an ejection of electron. So actually we can tell there is not time lag. We can tell like that. But this time lag you should know. Multiple choice and all that ask. What is the time lag? They will give the answers with different powers. So this you should know this. 10 raised to minus 9 second time lag. So these are the 4 laws. First law. First law. Ajmala, what is first law? അജ്മല വിളിച്ചിട്ട് വല്ല കാര്യമുണ്ടോ? അജ്മല ഇല്ല. അലൈഡ, അറിയുക? ഫാത്തിമ, ഫാത്തിമ ഇല്ലാത്ത പിള്ളേരോ ഒരെണ്ണമുണ്ട്. നീലിമ, വാട്ട് ഈസ് ഫസ്റ്റ് ലോ? Very bad if you behave like this. Saliha, what is first law? Saliha. Remisa, what is first law? വോയിസിനോട് ചോദിക്കുമ്പോൾ അവരെ ആൻസർ പറഞ്ഞു കാണിച്ചതാ. ഘനശ്യാം, വാട്ട് ഈസ് ഫസ്റ്റ് ലോ? ഘനശ്യാം, വാട്ട് ഈസ് ഫസ്റ്റ് ലോ?
Intensity of
incident radiation is
directly proportional to threshold frequency.
Photoelectric current. Very good. Intensity is directly proportional to photoelectric current. Then second law പറയുന്നത് എന്താണ്? Second law ചോദിക്കണ്ടേ? ആദിത്യൻ, second law ഗേൾസിനോട് ചോദിക്കൽ നിർത്തി. What is second law?
There exists a minimum frequency of incident radiation below which no emission of photoelectric electron.
There is no emission of photoelectron. Very good. There is that frequency is known as
threshold frequency.
Okay, very good. And above the threshold frequency, what happened? Arunjit, above the threshold frequency, kinetic
energy will only depend upon frequency of incident.
Very good. Boys are very good children. They answer all questions. I like that. Girls non answer at all. I don't know why they are not answer. Then last one. What is last one? There is no time lag between the incident of photon and the emission of electron. Okay, that is the fourth law. Next, Einstein's photoelectric equation. The same thing we are telling. Einstein photoelectric equation, very important equation. So that is what I told you. When h nu is the energy of the incident radiation, h nu. See, a photon of light of frequency nu, incident on a photosensitive metal surface, then h nu is its energy. Nu is the frequency of the incident radiation. Therefore, what is the energy? E equal to h nu. But when h nu energy is incident on a metal surface, I told you work function of the metal is there, h nu 0. Work function. And that energy, it will, from this incident radiation, it will take h nu 0 to eject electron. And what happened to the remaining energy? Remaining energy is converted into kinetic energy. So, incident radiation is having energy h nu. From that, the metal take h nu 0 to eject electron, and the remaining energy is converted into kinetic energy. What is the equation for kinetic energy? Half mv square. So, same equation we can see. See, h nu is the energy incident. In that, h nu 0 is taken to eject electron, and the remaining energy is kinetic energy, half mv max square, maximum kinetic energy it will move. So we can write this taken to left side, h nu minus h nu 0 equal to half mv max square. H into nu minus nu 0 equal to half mv max square. Understand? So this is the Einstein's photoelectric equation. So that is explained here. From the energy h nu, a part of the energy is used for liberating the electron from the metal surface, which is also equal to the work function of the metal. The rest of the energy of the photon is used in imparting kinetic energy to the, yes? Huh? Screen കാണില്ലേ? ഓക്കെ നോക്കട്ടെ.
ശരിയാണ്, സ്ക്രീൻ കാണുന്നില്ല.
ഓക്കെ, sharing point. Okay. Now can you see? Children?
Yes, teacher.
Okay.
Yes,
Okay.
teacher.
Okay. So here, this is h nu is the energy of the incident radiation. From that, how much energy it will take to the electron? That is the work that depends on the work function of the metal. And from that h nu 0, it will take to eject electron, because incident energy is greater than the threshold energy. So from that h nu 0, it will take to eject electron, and the remaining energy will be in the form of kinetic energy, half mv max square. So h nu minus h nu 0 equal to half mv max square, and h into nu minus nu 0 equal to half mv max square, where nu is the energy of the incident radiation, which is greater than the threshold. Sorry, nu is the frequency of the incident radiation, and nu 0 is the threshold frequency of the radiation. Then V max is the kinetic, velocity, half mv max square kinetic energy. V max is the maximum velocity of the electron. Okay, this is Einstein's photoelectric equation. What is h here? Planck's constant. H is Planck's constant. Nu, frequency of the incident radiation. Nu 0, threshold frequency. M, mass of the electron. V, velocity of the electron. Okay. Explanation of laws of photoelectric equation. Always remember, very important equation, Einstein's photoelectric equation. Problems also you can expect. From all formulas you can expect problems. Explanation of laws of photoelectric emission on the basis of Einstein's photoelectric equation. So 4 laws we have studied, and those laws are explained on the basis of this equation. Let us see that. Okay, first law we know intensity is directly proportional to photoelectric current. For the explanation for that law, according to this Einstein's photoelectric equation, all the 4 laws are explained on the basis of that. Laws of photoelectric effect is explained using Einstein's photoelectric equation. If the intensity of the incident light increases, the number of incident photon increases, which result in increase in the photoelectrons, and therefore photoelectric current increases. That is very simple. As the intensity increases, that means more number of photons are incident. That is the meaning. So what happened? One photon is incident, one electron will be ejected. That is actually taking place. When one photon is incident, one electron is ejected. So more photons are incident, more electrons will be ejected. So when intensity increases, more photons are incident. Therefore, more electrons are ejected. So just a simple thing. Then nu less than nu, second law is that when the frequency is less than the threshold frequency, no emission of photoelectron takes place. That also is explained. If nu is less than nu zero, in the equation you see, this is our equation. This is our equation, Einstein's photoelectric equation. Nu is less than nu zero. Nu zero is the threshold frequency. If the incident frequency is less than threshold frequency, we know there is no emission of photoelectron. That means kinetic energy becomes negative. See, nu less than nu zero. Kinetic energy, this is the case. Nu less than nu zero, nu ചെറുതായിഞ്ഞാൽ അതായത് ചെറുതിന്ന് വലിയത് മൈനസ് ചെയ്യണം ന്യൂ ചെറുതായി കഴിയുമ്പോൾ ഇത് ചെറുതാവില്ലേ അപ്പൊ ചെറുതിന്ന് വലിയത് മൈനസ് ചെയ്യുമ്പോൾ എന്തായി നെഗറ്റീവായി നെഗറ്റീവ് കൈനറ്റിക് എനർജി ഇസ് നെഗറ്റീവ് വിച്ച് ഈസ് ഇമ്പോസിബിൾ കൈനറ്റിക് എനർജി ഈസ് ഓൾവേസ് പോസിറ്റീവ് ക്വാണ്ടിറ്റി സോ വിച്ച് ഈസ് ഇമ്പോസിബിൾ അപ്പൊ അതായിരുന്നു തേർഡ് ലോ പറയുന്നത് തേർഡ് ലോ അല്ല സെക്കൻഡ് ലോ അല്ലേ സെക്കൻഡ് ലോ പറയുന്നത് അപ്പൊ ഇഫ് ന്യൂ ഇസ് ലെസ് ദാൻ ന്യൂ സീറോ കൈനറ്റിക് എനർജി ഈസ് നെഗറ്റീവ് which is not possible. Apart നമുക്ക് പറയാം less than the threshold frequency there is no emission of photoelectron. അപ്പോൾ അതാണ് എക്സ്പ്ലെയിൻ ചെയ്യുന്നത്. ഇനി തേർഡ് ലോ അത് ഇത് തന്നെ വെച്ച് എക്സ്പ്ലെയിൻ ചെയ്യുന്നില്ല. തേർഡ് ലോ അതായത് ഇഫ് ന്യൂ ഇസ് ഗ്രേറ്റർ ദാൻ ന്യൂ സീറോ അപ്പോൾ വലിയതിൽ നിന്ന് ചെറുത് മൈനസ് ചെയ്യണം. ന്യൂ ഇസ് ഗ്രേറ്റർ ദാൻ ന്യൂ സീറോ അപ്പോൾ ഗ്രേറ്റർ ക്വാണ്ടിറ്റിയിൽ നിന്ന് സ്മോളർ ക്വാണ്ടിറ്റിയാണ് നമ്മൾ മൈനസ് ചെയ്യുന്നത്. അപ്പോൾ കൈനറ്റിക് എനർജി പോസിറ്റീവ്. Therefore, what happened? Greater than the threshold frequency. If the incident radiation is greater than the threshold frequency, the kinetic energy is positive. So that is possible, directly proportional also. Frequency is greater than the threshold frequency, kinetic energy is directly proportional to frequency. That explanation. And the last one, there is no time lag, or there is a very small time lag between incident of photon and the ejection of electron. So just when that is an instantaneous process, just when a photon is incident, the electrons are ejected. So that is an instantaneous process. According to Einstein also, he also said like that there is no time lag between incident of photon and the ejection of electron. That also explained. അപ്പോൾ അങ്ങനെ നമ്മൾ 4 ലോയും നമ്മൾ എക്സ്പ്ലെയിൻ ചെയ്തിട്ടുണ്ട്. നെക്സ്റ്റ് Next, photoelectric emission is accounted by quantum theory of light. That is particle nature of light. That is an important point. Photoelectric emission is accounted by quantum theory of light and particle nature of light. Sharing this point. Then relation between cutoff potential, this is next is relation. This is nothing new, the same thing. We are writing in different forms. Same thing, Einstein's photoelectric equation. Because for doing problems, different types of equations we should know. That's why. The relation between cutoff potential means stopping potential. Frequency of the incident radiation, nu, and the threshold frequency, nu zero. Relation between them. And you see Einstein's photoelectric equation, kinetic energy maximum equal to h nu minus h nu zero, or h nu minus w zero. H nu zero is same as w zero, work function. So half mv max square equal to h into nu minus nu zero. Therefore, we know half mv max square is ev zero. E is the charge of the electron. E zero is the stopping potential applied. So when stopping potential applied, all the electrons are stopped. Maximum kinetic energy is converted into potential energy. That is why we have taken equal. When we apply a stopping potential, all the electrons are stopped. That means kinetic energy is stopped. Then only it will have potential energy. When kinetic energy is stopped, it will have only potential energy. Electrons is the charge of the electron. V0 is the stopping potential applied. So kinetic energy is completely stopped. That will be potential energy itself, EV0. EV0 equal to h into nu minus nu 0. Therefore, EV0 equal to hc, nu equal to c by lambda. Nu equal to c by lambda. C is the velocity of light and lambda is the wavelength of the light. 1 minus 1 by lambda minus 1 by lambda 0. So EV0 equal to hc into 1 by lambda minus 1 by lambda 0. This is in terms of wavelength, this equation. This is in terms of frequency. So different forms, the Einstein's equation we are writing in different form. Okay. Determination of Planck's constant and work function of the metal, that is from the graph. You can see this equation. Half mv max Einstein's photoelectric equation. Half mv max square equal to h into nu minus nu 0. And we know half mv max square is EV0. Just now I told you. Kinetic energy is equal to potential energy when it is stopped. V0 is the stopping potential. We cannot write V. V0 is the stopping potential applied. Then only this becomes equal to half mv max square. So that's equal to EV0. So EV0 equal to h into nu minus nu 0. V0 equal to h by E into nu minus W0 by same thing we have studied, but it is used for different purposes. So here V0 equal to h by E into nu minus W0 by E for answering the questions. I am explaining all this. Different type from the graph, find out frequency and stopping potential graph, find out Planck's constant. Such questions will come. Planck's constant we can find out work function. Such problems will be there. Graph also itself, graph itself asked for that. Same thing, studied things we are explaining in different ways. So here we are finding the Planck's constant and work function from this graph. This is the frequency stopping potential graph that we have seen. There exists a minimum frequency below which there is no emission of photoelectron. Above the threshold frequency, they are directly proportional. This we have seen, this graph. And we are finding the slope of this graph to get the Planck's constant. And for that, this equation we are writing in the equation as an equation of straight line. Equation of straight line. So V0 equal to h by E into only finding h by E into nu minus W0 by E. So E is taken to right side. Nu 0, h nu 0, that is W0, work function. Then this is the equation of a straight line. You see this form, y equal to mx plus c form. This is the equation of a straight line, y equal to mx plus c. So here what is m? The graph is between y and x. Yeah, the graph is between V0 and nu. So m is slope of the graph. So here what is the slope? H by E. So by finding the slope of the graph, you will get h by E. H is Planck's constant, E is the charge of electron. And by finding the y-intercept, we can find out this work function. Y-intercept, C, that finding C. Y-intercept, we can find out the work function of the method from this graph. So we have plotted the graph between frequency and stopping potential, and we just find the slope of this graph. So for how will you find slope? You take any 2 points on this graph. Any 2 points you can take because it is a straight line. Any 2 points you can take and you can complete this triangle, and this difference, draw lines from this point to this V0 axis, and from here you draw a line to the V0 axis to find the difference of that. For example, suppose this is minus 6 and this is minus 4. You can take the difference of that, 6 minus 4, 2. That is delta V0. Similarly, here also you draw perpendiculars to the x-axis. That will be the change in frequency. For example, this is 5 into 10 raised to 14. This is 7 into 10 raised to 14 hertz. Then you can find the difference too. That will be delta nu. So this difference will give delta V0 and this difference will give delta nu. Then slope means tan theta. Tan theta equal to y by x. Delta V0 by delta nu. Delta V0 by delta nu, that is tan theta. That is equal to, we know, slope of the graph gives h by e. So slope is this, that gives h by e. So h equal to e tan theta. Tan theta we have calculated, we have the values here. So you have just to find tan theta from the values. And you just substitute, is the charge of electron. Charge of electron into tan theta will give Planck's constant. Similarly, work function also you can find. You just extend the graph to meet on the y-axis. So the y-intercept, that is means this OC part. For example, this is 5 EV, like that is our value we are getting, potentials 5 volt we are getting. So that 5 will be minus W0 by 5 minus 5. So that will give W0 by E. So W0 work function, how will you find? E into that y-intercept. E into that y-intercept. If it is 5, E into 5. Like that. So according to equation 1, graph between V0 and V nu is a straight line having slope h by E and y-intercept is minus W0 by E as shown in figure. Work function W0 will be equal to E into OC. OC is the y-intercept. Suppose we are getting 10, we have 10. E into magnitude of the intercept, magnitude only. Magnitude of the intercept on potential axis. So from this graph, we can find out, by finding the slope, we get Planck's constant, and by finding the y-intercept, we get work function of the method. You can expect problems.